Thank you, Hidayat. Welcome to session 11. And yeah, thanks today to our volunteers, Hidayat, Nastasia, Guillem, Lily. I think I've got all our volunteers today, and Thomas. Thank you for making this happen. Go, Guillem.
And Sid also.
And me. Thank you. And with that, I will hand it over to Nastasia. We're going to do a short presentation on signals, and we'll have a little Q&A after that. Guillem's then going to show us CAP grants, capability grants using the Holochain gym, which I'm kind of excited to see. I haven't seen it on Holochain gym myself. And we'll do a little Q&A, and then we'll do a code review of signals implementation, and then probably go into the break with some more Q&A after that. So over to you, Nastasia.
Thank you, Sid. A second, I would share my screen. Can you see it?
Yes.
Yep.
Okay, cool. So today we're talking about signals, which are a fast communication tool provided by Holochain. So signals are very quick, meaning that they are almost real time. And this is partly because they are not published to DHT or source chain. So this is a node-to-node, sometimes node-to-node communication, which goes directly and is not persisted. And every signal can contain an arbitrary data inside. So it's up for you as a developer to define what kind of data can be sent in a signal. So you can use them as a way to quickly exchange some data, which is not mission critical and can be lost if something goes wrong. That's because signals are fire and forget, meaning that there is no confirmation of receiving a signal from the agent or some other target to which you are sending the signal. You basically like UDP. So signals are a handy tool when it comes to updating your application to make it more responsive and making it more interactive for the users and for the backend UI interaction as well. So with signals, we have two types of those. There are local signals, which are sent from the backend node, so from the Holochain conductor to the user interface. Those are aimed to make your user interface more responsive. And instead of having to pull for some data regularly from the user interface to the backend, you can just simply listen on the WebSocket connection for any events as in signals that would come from the backend. And so you can react on those events when they come. And once again, it's up for you to define how would this reaction happen. And then there is another type of signals, which is remote signals. Those are sent between the Holochain nodes, so between the Holochain conductors. And those are, this is the actual type of signal which is used for fast communication between the Holochain agents. And they are not persisted to DHT and source chain in both cases. When working with signals, there are two most typical errors or caveats that you may experience. So first one is that I've already mentioned. Signals are fire and forget, so you should not be relying only on them for any critical data. For example, if you want to notify your user about some event, and it's critical that user is aware of this event happening, then you would be better equipped in implementing this event both as something that's published to DHT and then as a signal which complements this publishing, meaning that when you publish something to DHT, it would take some time for data to propagate. So user may not learn about this for some time. But then if you add a signal to this, then user can be instantly made aware of something happening in the application. And then they can wait for the data propagation to happen, which brings me to the second point. Since signals allow you to work faster than data propagation happens in DHT, it's very commonly possible, and we've encountered this problem during the DevCamp game development, for you to receive some hash of data via signal, which you do not yet have in your own chunk of DHT, because data propagation didn't finish yet. So you already know the idea of the data, but you do not have the data itself. So if you try to do a query in this kind of situation, you would get a DHT retrieval error, which by itself isn't a problem. The problem is that if you as a developer do not expect this to happen, then your application would fail. So if you are working with any data that you receive from signals, you should be taking care of those problems and implement some retries or change your logic in some other way to make sure that you do not fail into this trap. And that's basically it. That's a very short intro in signals. And we would be talking more about them when we show the code, how we implement signals handling both local and remote in our game of commands for the DevCamp. So that's it.
Thank you. We don't have any questions yet. Do you want to share a little bit, Nastasia, about do nodes have to be online for a signal to go through?
Right. Yes. So node has to be online to receive the signal. And if it's not, you wouldn't even know about it. So you send your signal and you hope that the other node that you want to receive the signal would be online. But if it's not, that's where it's important to complement your data sent over the signal with something that's published to DHT, because then some other nodes would propagate this data. So the target nodes comes online after some time, and then it would receive the DHT data, but it wouldn't receive the signal.
Cool. And can you share some examples of where signals might be useful compared to just DHT propagation?
Yeah, so for example, if you have any events in your application that you want to catch instead of having to poll for them, in our game, for example, we are starting the game session, we have the game rounds. So once the game session is started, every player can make their move. And there are two ways for a player to learn about this event happening. First one is they could receive a DHT entry for the game session. That would take some time. And while this is happening, their user interface would have to constantly poll for new data from the backend. So basically make a query to DHT. Is data here yet? No. Okay, we wait again. But then if we add signals to this scheme, then we can instantly notify people that they can make their moves, which would make for a better user experience.
We can actually move to the next session, which is Guillem taking us through capability grants with the Holochain gym. Cool. Let's move to the next session.
Okay, so, I cannot share my screen. Sorry. Yeah, perfect, thanks. Can you see my screen? Yep, okay. Yep. So what I'm looking at is in the Holochain gym. So it's a bit varied if you don't know your way around it. I can share the link after. But it's basically start your workout, which are the actual exercises focusing on each of the features and capability tokens, right? And this is really simple. Like the interaction that I have here is really simple, but I think it's just enough for me to explain what are capability tokens. So what are capability tokens? Capability tokens are the unified security system of Holochain, basically, which means that everything that is related to authorization needs to go through capability grants. And Holochain has a very clear distinction between identification and authorization, right? So here we are talking about, do you have the right to execute this code or not, right? So this is what we are talking about. A capability token is really just an entry. At the end of the day, it's just an entry that you commit to your source chain saying these agents have the right to call these functions, right? Let's go through an example, an interaction, to basically get a grasp of what the capability token is used for. So actually this example, we have a Goldie, such weird names come out of this library, Goldie, and then Myrna. I'm sorry if someone is called Goldie or Myrna. Those names are fine too. So Goldie and Myrna are those agents, two agents, sorry, playing in the same DNA, right? And Goldie wants to notify Myrna of something, maybe call some function, maybe send a signal, maybe, whatever it is that one agent wants to do to another agent. That's when you need capability grants. In this case, Goldie wants to call a function in Myrna's node, right? So remember, this is only possible. They can only see each other if they are playing inside the same DHT. Okay, so let's run through it. Let's say that they are, at the beginning, they have installed the DNA and nothing else, right? So they haven't done anything else in this DNA. So first step, Myrna tries to do a remote call on Goldie's sample zone function. So Myrna wants to call sample, as a sample is the zone function name, in Goldie's node, right? So maybe sample is a way to get private data, maybe it's a way to notify Goldie, whatever. It could be arbitrary code, like it's the same as we have been seeing defining HDK external functions. Okay, so let's see what happens. It tries to execute the call remote. Call remote is the name that we give when a node tries to execute a function in another node. And what Goldie does is it tries to call unauthorized, right? So what's happening here is that Goldie hasn't committed a capability token for Myrna to call the function, the sample function, the sample function, right? So what this means is that Holochain has basically a restrictive security system in which if you don't give explicit capability tokens, explicit calling rights to other agents, by default, no one can call anything, right? So Myrna cannot actually call anything, any function in Goldie's agent until Goldie has given capability, the appropriate capability token, right? So Myrna now says, hey, Goldie, I want to call this function. They are saying offline or whatever. But you haven't authorized me calling your function. So Goldie says, okay, I'll create a capability token that will let you call my function, right? And this is an entry that it's created. Capability tokens are always private, right? So they don't go to the DHT, they stay in the source chain. So it just creates a capability token in its source chain, that's fine. And now Myrna tries to call the same zone function and as they were trying to call the first time. Let's see what happens now. Cool, and now Myrna can call the sample zone function from Goldie because Goldie Holochain, and this is done automatically, Holochain goes through the source chain of Goldie to see if there are capability tokens for the incoming call. Okay, but what if now Goldie says, no, wait, this is giving some private information. I don't want Myrna to be able to call this function in my node anymore. So capability tokens can be revoked. So you can say revoke capability token. Inside like Goldie is the one that has granted the capability token, so they can also revoke it. And this is just the same way as you create capabilities grants private in your source chain, you revoke those capability grants exactly the same way privately in your source chain. So it doesn't go actually to the DHT. So let's see. Goldie calls revoke capability in their private source chain. Success, obviously, because it doesn't need any authorization from anyone to revoke a capability which is private. Okay, and now Myrna tries to call the zone function again. So I guess you can guess what is going to happen, which is Holochain is going to go through the source chain and see, okay, there was a capability token, but then it was revoked. So actually, Myrna has no rights to call the sample some function in Goldie's node, right? So now Myrna just can't do anything about it, right? So this is it, really. This is a very, very simple interaction to serve as a way to for you to get like the tree, because capability tokens normally confuse a lot. Like it's a bit disorienting, as in, okay, what do you mean by a token? Capabilities mean different things in different systems. So just think that it's really a way to grant permissions for other agents to call your some functions. And really, that's the use case that we have shown, but you can think that that's the unified security system of Holochain. So no matter from where the call is coming, the same system will work. As in, if it's a bridge call, which we are going to talk about later, of UI or whatever, it's all controlled by capability tokens in this exact same way, right? No matter where it's coming from. Going to stop there?
I have a question. Are these capability tokens on function level, or you can grant to another node rights to, execute everything that you have, all the functions?
Really good question. So here, little down below, you can see what's a capability grant in Rust, like it's a Rust track at the end of the day. And here, the capability access, you can define different capability access types. So what you cannot do is grant to any function you have. You have to specify the specific, the explicit functions that the capability token is going to authorize, right? The functions have to be specified. But about the agents, you can say unrestricted. So any agent can call these two functions, right? You can say assign, which is only Alice and Bob can call these two functions. Or you can say transferable. Anyone that has that this password can call these two functions, right? So if let's say that, for example, I want to do transferable and the password is hello, I say, okay, grant capability for this function with password hello, and I give the password hello to Alice. I am also allowing Alice to share the password hello to Bob, and then Bob can also call my my function with that secret, right? In here, the secret is just a password, and anyone that has the password can really call.
Okay, thank you.
Cool.
Thanks. I think we're getting.
Why do you need a secret when you specify already the list of agents?
You don't need a secret. You need a secret only if you want to allow anyone that has the secret. Like it's a mechanism. You have to choose one mechanism out of three, right? So you could choose unrestricted, which is no secret and no agent list. So whoever is calling these functions is going to work. You can do. Sorry, you are okay. You're referring to this one. Okay. Sorry. I get the question now. Here you could say also without like password none, right? There is a way in which you say really that there is no secret here. That's a good question. It's a bit weird, but it has some utility as well. As in, okay, maybe there are some assignees that don't have yet the password, and you only want them to be able to call the function when they get the secret, right? So it's a bit like transferable, but with a whitelist of all the agents that would possibly get the password. This is provided this has, I think, limited use cases, like narrow use cases, I think.
Thanks. We have a question in Discord. In which cases do we need call functions of other nodes? Can you give some examples? Yeah, good question.
Yeah, I can. Good question,
Sure.
because I wanted to add something here that the question came. One of the use case you see, as Nastasia mentioned, it is the pinging, signaling each other just for the better performance, better UI, actually, the user experience. One of the most famous one that you might need it is subscription. So in the peer-to-peer world, if you would like to provide some content, and I'm supposed to pay you monthly to receive your new Bella, your new content. So you can provide a subscription using a capability token. You make all your content private in your chain, in your machine. So you give me permission or a capability that every month, if I did payment, I can call your function, that your function provide me some private content, that it is not DHT. One of the most interesting use case that I've been faced, it is subscription.
I guess other examples we could also think of are any kind of reputation data, like you might have transactions that you might, maybe loan repayments or validations like likes or claps that you might have received. And you might want to give access to that to someone. But of course, the caveat here is it's on your source chain. So it might be a very specific use case. But yeah, I think the list is endless.
There is also the simplest use case that we are actually going to show. You need the smallest allow all capability token to use signals. So we would show how to make this token and then how to receive and send signals from the backend. And if there are no more questions about cap tokens, I propose we go to the code review. Can you allow me to share the screen again? I dropped, so I lost my permissions. Thank you. Okay. So let me start my Visual Studio. So I wouldn't be switching between the comments today. I would just show different parts of the code in the order which makes sense from the logical perspective. So give me a few seconds while this is loading. So the first thing that we want to do, so here we are defining signals. Yeah.
Before starting, would you please show people that where are the places of GitHub repository and which branch?
Oh, I've already shared a link to this code in the Discord channel and I pinned the message.
Okay, because for the video, the people who are going to see somehow video without accessing to channels.
Yeah, so that's the repository from which I'm doing this. Yeah, is it enough?
Great, thank you.
Okay, cool. All right, so today we are adding signals to the game that's already fully implemented and working, including the validation. So first thing we want to do is define types of signals that we would have in our application. And the game signal enum is doing exactly that. From this enum definition, you can see that we would have 4 types of signals: player joined, start game, start next round, and game over. You can also see that every enum value contains something inside of it, basically a signal data that would be shared between the nodes. So for the player joined, we would actually just send the player profile of somebody who has just joined the game, because it contains a very small piece of data and would allow both to know the nickname for user interface purposes and also to know the public key of the agent. Just as a reminder, the player profile struct looks Rust analyzes loading. Okay, so player profile only has 2 fields. And then for the rest of those signals, we can do with a single data type, which we called signal payload. It wouldn't be that different because for any kind of event, for events of starting game, new round, and game over, we would always want to know the session hash, because this is what allows us to get more data about this game. And the entry hash of the last round that has been actual for this event. So for example, for the start game, we would be providing round hash of the first round, for the start next round of the one for which you have to make your moves. And then for the game over, it would be the last round that has been played in the game. And this is how we pack our data about game session entry hash and round entry. As usual, since we would be sending this data across between backend and frontend, we would need to apply these derive traits, which are needed to serialize this data and to be able to display it properly. And then you can also notice that here we need to provide additional fields to simplify the serialization of this enum. Serde is not Holochain related library. It's a Rust library, which you can read more about. It's a huge one, which handles a lot of data working for Rust applications. So now that we have those data types defined and we know what kind of signals we want to send in our application, it is time for us to set up the functions which would allow us to actually send those signals and to receive them, which is much more important. So first thing that I would need to add is I would add a function called init, which is a callback of any Holochain application. Before this, we didn't need to do anything on this step of loading the Holochain application, so we didn't define this callback. It's an optional one. But now that we want to set up the signal setup, we need to do this in this callback. So first we would be defining signals, which is first we would be defining the capability grants, which we actually need in order to send the signals. Why is that? Every time we receive a signal, we would need a handler for the signal to process it. And this handler would have to be a function, a zone function, which is defined on our side and which has to have some access to it. And this function is defined here. And that's a small one which would, that's a small function which would receive data of the signal in the format as we receive it. I mean, it's not a Rust struct which is properly serialized. That's for us to do. So we just receive the raw data of the signal and we try to decode it on this line. As you can see, we are specifying the type parameter for the decode, saying that we want to obtain a result, which would contain a game signal instance if it's okay. I mean, if the result is successful. And if there are any problems, we would get some kind of error of the serialized bytes error type. So we are getting this signal result. And then at this point in time, we do not know yet if it's okay or if it's a fail. So here, using the typical Rust idiom, we are matching the game signal result to two different values. First value is, okay, which contains inside of it the game signal instance, which we called A in this case. And if that's okay, and we have decoded everything correctly, we are now emitting a local signal. So this handler function is receiving remote signals from other Holochain nodes. And if everything is okay and signal can be recognized, then it emits a signal local to the user interface, so it can react on it in appropriate way. And if we encounter any problems when deserializing our signal, then we just return an error for the local conductor, meaning this error wouldn't be sent to the agent who sent us the signal. It would just go to the logs of the current node for which this receive remote signal is being executed. So we have this receive remote signal, but we cannot let any agent to access this function for us unless we define a capability token grant for doing so. So I'm going back to the init callback to pick up where I left. Yep.
Can you go back to the function?
Yep.
So the question that it means this function reqv remote signal. It is in the conductor of the agent that receive a signal from the conductor of another agent.
Mm-hmm.
And when it is received, emitting signal is telling, hey, call my UI to refresh something. Am I right?
Yep.
Yeah, that's great. It means generally when agents talking to each other, the UI are not talking to each other. Conductors are talking to each other. Yes?
Yeah. Thank you for the clarification. Yeah. UI is only receiving signals we send from here, and it's only receiving signals from the local conductor, so the one on which the current agent is running. Your user interface wouldn't receive signal from any other agent's conductors directly. It can only receive signals from the local conductor to which it's talking. Anything else?
No, that's it. Is there any questions so far?
Yeah, we can pause for questions. I mean,
I have one.
No.
The receive remote signal, this function is it's a naming convention, and that is enough to receive to know that this is the call that will be done anytime any signal will be received.
Yeah, that's the thing. This function is needed to handle the receiving of the signal, but you wouldn't be able to execute this function if you do not define a capability token, to which I'm getting to right now after we handle the questions.
But this function has to be named exactly this way.
Oh, no. The name is absolutely custom, so you can define it as you wish.
Can you show where? Can you show where it is? It is. You can define. It is the.
Yeah.
No, it is not a naming convention. It means like a validation that you need to follow a convention. You can specify what is the function and when to call it. Yes, we are going to see it.
Yeah. So here you can see that I am specifying name of this function exactly as it's written in my code. When creating a B-tree set of functions to which I would be creating a capability grant entry. So let me walk you through what's happening here. First, the capability grant entry, the struct defined by Holochain, has, whoops, okay, that wasn't a good idea. All right, so we need to provide a B-tree set of functions that we want to cover in our capability grant. So that's why we define this one to be empty and mutable, because we would be inserting data into it. And then here I am saying that in the zone with the zone name like this, and this function resolves to the name of the current zone, you need to register this function with this name to be available later for the capability grant token. And at this point in time, I have just created a configuration for the cap grant, but I didn't do anything that would allow for signals to be received. Next step is to define the capability. No, there are actually two steps in one here. So here in the curly braces, I am creating an instance of the cap grab entry, which has empty tag because we wouldn't be needing to use it. I mean, our grant is very simple. It's very primitive. Its only purpose is to allow functions to be called, and we are not going to access it anywhere in our application. So tag is not needed. And then the access parameter is a Rust unit type, which is two blank braces. And then .into is just an explicit type conversion. So what this means is that since access is defined by a unit type, everybody would be granted this access. So we are not specifying exact agents who would be able to send us signals. We are saying that everybody can send us signals. And then as the last parameter for the capability grant entry, I am specifying the B-tree set of functions, which already contains our receive remote signal function. So from this moment, and then later, you can see that this all is wrapped into create cap grant function. So at this step, I am actually committing the capability grant entry to my source chain. And from this moment, so by the time we get to this line, provided that this entire function executes properly, the cap grant entry already would exist. So that's the first part about the capability grants. Are there any questions about it?
Yes, I have. So can we create a different function as a rim? It means, can I create a 4 or 5 function and open it with the capability, or I can just only define one function. And if it is more than one job, I need to put a switch case inside the function.
Oh, yes, of course, you can create multiple functions. So if I wanted to add another one, I would do another insert and provide here the zone name as I did before. And for example, I don't know, end game.
So the place that they are calling this one, they are calling by the function name. That is right, yes?
Mm-hmm. Yeah.
I have one more thing to add. It's regarding the question of Walter. Receive remote signal. You, like Nastasia showed, you can have different methods. But if you want to use remote signal, the HTK function, that is using this convention of receive remote signal.
Oh, Tim, thank you. Thank you so much.
I had to look it up myself, so I quickly checked in the source code of Holochain, and they're implementing this remote signal. They're just implementing it with these function calls and capability grants, and they just made a special implementations for this scenario. But you need to use this signature if you want to use remote signals. But I think I read somewhere in some posts of Paul that they're going to evolve this signal handling even more. So there will be changes in this part in the future as well. So
Thank you, Tim. That's a critical clarification. So far we have defined the capability grant entry that would allow us to receive remote signals. And now we would do the second thing, which, hold on a second, can you see my screen?
Yes. Yeah.
Okay, good. All right, so we've defined capability grant entry. Now we would do the second thing, which is not related to signals in any way, but doing it in the init callback is a good place to do. So that's what we would be doing. So we would set up a tracing configuration that would allow us to define a login level for our entire application. This is a code which is not directly related to Holochain. It's using the standard Rust libraries, which you would find in other projects as well. So what we're doing here, first step is we are creating a subscriber for our formatting. And this is a default subscriber builder here, to which we apply a chain of functions. So every dot you can see here is function being executed on the result of running the builder. First one, we are setting a level to be the trace one, which means that all events with a level higher than trace would be written to the std out, meaning that, well, it would be easier for us to log things in our application. And the next three steps are simple defaults for the formatter, which I wouldn't be covering in detail. And then after we apply all of this configuration, we just complete the builder, transforming it from the subscriber builder to the actual subscriber. And then once we finish doing this, we now run the set global default function from the tracing module, which we are importing here like this. So we are setting a global default with our subscriber, and if doing this action fails for any reason, we are defining using the standard Rust function called expect that this is the kind of error message that would appear if this action fails. That's just a small detail. This is not critical for any Holochain application, but if you want to have this configuration and to have it applied for the entire app, this is a good place to do this. Once we're finished with the second part and configuring our formatter, we can now return the OK result, inside of which we have one of the values possible for the init callback. Here's the thing, init callback itself in a Holochain application is such an important thing that it has its own enum for the return values that it could provide. And if I go to here, you can see that there are actually three possible values that init callback can return. And you can notice that there are unresolved dependencies here. This is, if I understand correctly, for the cases where on the initial step of your application, you need to verify something. And in order to do this, you need to obtain some entries. And so if those entries are not available to you just yet, you would be returning unresolved dependencies. But I'm not very certain about this step. So yeah, I wouldn't be talking about it. So we have written the init function, which allows us to receive remote signals. We have also defined the kinds of signals that we want to receive and send. Now it's up to us to actually send those signals. So now let's start with the player profile, which is, first one here. So our signal enum is here. And the first signal that we define is player joined. So let's go to the player profile to define the place where we send this signal. So first of all, this is our function join game with code, which we've written way back during the DevCamp. And this function would be pretty much left intact, except for first one, we would copy the input of this function into another variable input for signal. This is because input itself, if we do not copy it, if we do not clone it, we would partially consume the input variable here and then here. So by the time we execute this line, the input variable is no longer available. So we would need to clone its memory for us to access in the end of this function. Once we do this and define input for signal, we go way back to the end of the function. And we want to send the signal that player has joined. For simplicity, this code is separated into another function. And here it is. We are receiving the same input as join game with the code, because that's what we're working with. And first thing we do is we create a player profile with this input. We would need this instance to send it over the signal. Then we encode the player profile Rust structure that we have into the data for signal to be used. Next step is to obtain players to whom we want to send the signals. And we already have a function to obtain a list of players for the game code, so we just use this function. But here's a problem. We would receive the player profiles from this function, but we only need the pub keys of these players. So the next step here on this line, we are converting vector of player profile entries into a vector of agent pub keys. And to do so, we just receive a player profile entry, and from it, we only retrieve player ID. And we forget about the second field, which is called nickname, because we do not need it. After we got this list of player keys, we can actually send the signal. And in order to do this, we use an HDK provided function called remote signal. It would send signal with the data provided here to all the players identified by those pub keys in the vector. Once we send the signal and unpack its result by using this question mark, meaning that if this action fails, then this result would bubble up through this function to here and further on. Once we do this, we just return an empty OK result because there is nothing else for us to return. And that's how we send signals, basically. And the rest of the code would be kind of copying the same mechanism, but we would discuss how this is implemented for different parts of the game. So that's for player profile. Let's get back to the signal definition. Our next signal would be starting game. So let's go to the game session and scroll up for actually starting the game. So here's our function new session, which we've already also defined. This function, as well as the previous one for player profile, wouldn't be changed much, but I would just scroll down to the point where we've already created an entry. And this is what we add here. So before signals, this just didn't exist, and we would create a game session entry, create all links that it needs, and then return its hash. Now, just before returning the hash, we want to first create a signal payload packing all the data that we want to share with other agents. Here we have the game session entry hash and the entry hash of the round 0, which we're also returning from this function. Then we decode this data as a signal data. At this step, no signals are being sent anywhere. And then here is the next step. We want to only send signals to other players, but not to ourselves. So in order to do this, we need to filter ourselves from the list of all players who have registered to the game. And that's why I've defined another function called others. This is this function. It's very, very small and simple. What we do here, we receive vector of pub keys for all the players in the game. Then we get the pub key of the current agent, meaning the agent who is executing this function right now on the Holochain conductor. And then we just filter out this pub key from the vector. This is a idiomatic Rust code, more or less, because we get an iterator into the vector of players. We then apply filter to this iterator, and for every element in the for every item in the vector, we would call this not equal to me, and then collect the result as a vector of agent pub keys. So once we do this step of filtering, we have other players, meaning everyone except us. And then we just send the signal with the data that we've already encoded to all those players. And then we proceed to return the entry hash of the round 0. And are there any questions at this point?
Nope, we don't.
Okay.
Where do you put the name of actually the function for the remote signal? Because if we have a multi-function, I didn't see the name of.
Oh, yeah, we have, let me see. So here in the receive remote signal, we handle all kinds of signals in the same function. So you see, we get the game signal. We try to decode game signal, which is an enum, which would hold one or another value, one value at a time. And then we just emit the signal. If we wanted to, let's say, handle different kinds of game signal in a different way, we could do something like this. We could do a match to A, which is an instance of game signal, and then do something like this.
It means the receiver can just specify one function as a signaling, as an import, and if we need to have a different functionality, we need to put switch case to see which signal we receive.
Yeah, that is correct. Thank you. And then obviously, if you would have multiple enums like game signal and maybe, I don't know, player signal or whatever signal, then you probably want to handle those differently. Like here, we know that if we've decoded game signal, then we already have all kinds of signals that are possible in our application because we only have a single enum. I hope this makes sense. I have two other signals to show, but the code is pretty much the same. So if we want to end the game, that's what we do here. So first of all, this function ending game, we've originally defined it here with game session being empty. And now that we would actually send the signal, we would need this variable. So it now has a name. And then what else? And then in this function, we would add this piece of code, which again, we're creating the signal payload with entry hashes that we have in the function. And then we decode this payload to be sent as game over signal. And then we actually send the signal to all the game players. And yeah, this is another example where we are sending the signal to everyone, including ourselves, because we are not filtering ourselves from this list. We just take list of all players for the game session. And then the last signal for starting new round. Yeah, it's also pretty much similar. We are creating the signal payload with the data that we have already defined in the function for creating new round. We decode this payload as the start next round kind of signal, and then we send the signal to all the players registered for the game session. And yeah, that's for the signals on the backend. But there is also a bit that I have prepared for the tests, which are basically kind of like a user interface. So first of all, I would show the tests. Just wait a second. Okay, so these are the tests from the previous sessions without that many changes, except for those lines. So here you can see that we are defining a signal handlers. This one is defined for Alice. And inside of the handler, let me scroll here. Yeah, so this is just a handler which receives a signal. Inside of the handler, we are unpacking its payload. We are printing this payload to the output, kind of doing it twice, like this is how you do it if you want to add a comment. T.OK verifies that the payload is actually okay, meaning that it's not an error. And this one actually outputs data to the output of our tests, and that's what we would see when running those. And this is an example of how to unpack data from this payload. So here, round hash from signal isn't being actually used, but if you wanted to extract data from your signals, that's how you would do it. So for the signal variable that your handler would receive, you would access its data.payload.signal payload, and then you would get the actual field of the Rust structure that we packed on the backend. We do the same thing for Bob, except for him, we're not showing how to unpack data twice. And then there is the last step, which is critical for actually executing those promises, which we add here. So I am not adding these awaits right in the beginning, because if I do this before any signals are being sent, I would just be waiting forever. But I am honestly not sure if it's the best way to do this. So, I mean, this is currently working. That's all I can say. And now that we've added those things, I want to show you how this looks while we are executing the tests. So now, apart from having all of the output that we had previously, we would also see contents of signals, and we would instantly know when during the execution we have received those signals. We, as a user interface, that's executing tests on the backend. Yeah, I forgot I've been making some changes, so it needs to recompile. Shouldn't take long. So while the tests are running, you can already start typing your questions, because after I show how it looks, this part would be done. So the tests have started their execution. The conductors for players are being spawned. And now everything is happening fast, so I would scroll up to show it in the process. So first, what's happening here? We can see that Alice created the game code, and then she joins the game code according. This is the debug output that we have written in our backend. And then, so a lot of things are happening with this part. We see that her player profile is being created, and now Bob is also joining the game. And now you can see that Alice has received a signal about Alice joining the game. And if we go further, we can see that Bob has received signals about Bob joining the game, and Alice received the signal as well. So as the tests execute, yeah, so that's the list of players. Yeah, So now we defined in our tests. Let me show how it looks here. Starting game. Yeah, so you can see here on my editor that Alice is the one who is calling start game session with code, which means that Bob would receive a signal about game being started because he cannot start the game. So that's how his signal payload would look. You see the entry hashes of both game session and round zero.
We actually left so much out of the picture that we didn't actually have time to show you. So don't worry, you have the basics. Like with this, you can already build, I think, 80%, 70-80% of all applications. But there are some applications and some specific use cases that requires very specific features, right, that you won't need in every Holochain application. So I want to just give a brief overview of the complementary features that you have in Holochain. So only so that you know about them, and at some point you could look at the documentation and start using them, right? So that's the idea, is to just give a brief overview of those. Can you hear me well? Because my Zoom is, yeah, okay, cool. Okay, sorry about that. Okay, so I'm going to share this link later. Can you see my screen well?
Yep.
Cool. So things that you can do in Holochain that we haven't covered up until now, right? So this is the list of things, and then I've tried to, at every feature, have a link to the HDK so that you could go further and say, okay, I need this now. Let me look at the documentation. Let me start using it. It could be useful also to have examples of this, but I'm afraid I don't think there is enough of examples in the community, because some of these features are really fresh, and we don't have enough examples yet. So let me run through it quickly, and then maybe a couple of questions, but I don't want to do this in any kind of detail. Okay. So first of all, we can encrypt and sign things, right? So we have public and private keys. So the most basic thing that you can do with public and private keys is encrypt things, data, arbitrary data, and sign things, right? So you have functions in the SDK to encrypt, you have functions in the SDK to sign, right? Really simple ones, and these are not creating anything in the DHT. It's up to you to say, okay, I'm going to encrypt this content and then publish it to the DHT. That's totally fine. Another one is breach calls, right? So in the content of the DevCamp, we have covered basically one application, and inside that application, one DNA only, but there may be applications in which you want to have more than one DNA, right? So I don't know, you can have a YouTube clone in which the file storage is provided by a complementary DNA, not the main one, right? So now the question is, okay, but how do we communicate one DNA with another one, right? So this is where breach calls come in, which is basically a call of a function from one DNA to another DNA. The really important thing is that these two DNAs need to be in the same conductor, right? So I can't call another DNA that I don't have installed. I have to call a DNA that I do have installed. If I want to get data from a DNA I don't have installed, I actually need to ask that data to someone who actually has that DNA installed, right? So that's the dynamic. That's a whole kind of worm, so I don't want to get too detailed into it again, but just to know that this is possible. Call remote, I think we have covered it. Inside the same DNA, you can call from one agent to another agent, right? Counter signature is a cool feature that has come out like, I don't know, 2 weeks ago, which is a way built into Holochain to have an entry be created by multiple parties, right? So imagine a mutual credit transaction in which I want to transfer some credits to Nastasia. this is a way to say, okay, this transaction is only valid if both of the parties accept it, right? That's basic idea. And you could have not only two parties, but n parties, and like it's all there. The mechanisms are there for you to use. Another one is scheduling. Scheduling, I think it's pronounced. Scheduling a function execution in the future. So this is useful, I don't know, if you want to be indexing some entries, but you want to do it every week, every day. I don't know, there are multiple use cases that could fit here. So basically you have a way to say, okay, execute this function every 5 minutes or every day or whatever. Important, the function will not be executed if the node is not online, obviously. So you have to be online for the function to be executed. Next are membrane proofs, which is arbitrary data that the DNA can require for you to join a network. This is one of the most important concepts actually when we get to multi-DNA architectures, because this is the main way you can allow some agents and disallow some other agents from entering a network, right? So an example, let's say that my DNA requires a ticket signed by some authority. So for example, this is a private course and the teacher of the course needs to sign a ticket to the participant in order for the participant to enter, right? So in this case, the membrane proof would be the ticket signed by the teacher, proving that the teacher has given permission to the student to for participating in the network. Next are DNA properties, which are, this is arbitrary key value pairs from which you can configure your DNA. Really. It's really an easy way to say, for example, let's say that I have, I don't know, a mutual credit DNA, and I want to set the negative credit limit to 100. I can have a DNA property and I can say, okay, please install this application with these properties, right? This is a really easy way to change the behavior of the DNA without having to recompile the code, right? So I can give you the code and you can instantiate different networks with that same code and different properties, right? Importantly, the properties affect the hash of the DNA, right? So you can have two DNAs with the same code and different properties, and that will be two DNAs, two separate networks, right? Because the properties also get hashed when we are computing the DNA hash. So if you change the properties, you are playing another game. This is another DNA, this is another network. And then lastly, we have cloning DNAs, which is just getting the same code that we had for a DNA, changing some properties and instantiating, creating a new network out of that DNA code and those properties. This is known as cloning in Holochain, and this is used in Acorn, for example. So in Acorn, if you don't know what it is, it's a project-based task management system in which every project is its own DNA. So basically what Connor is doing with Acorn is cloning the project DNA with slightly different properties. So you get this multi-network application in which you are only participating in the networks of the projects that you have already joined. So this is quite interesting. And the last one I didn't remember to put in actually is post-commit, which is a callback that you can that is going to be run after any entry has been created. So you can, I don't know, in our case, it could be like, okay, create a game move, and after the game move has been created and validating and everything else, in post-commit, you emit the signal, right? These kinds of use cases would be fit here. Okay, this is it. are there any high-level questions, not detailed, technical, whatever, but more about the big picture and how these features fit in the Holochain ecosystem?
Thank you very much. Thanks for joining. Thanks to all the volunteers for helping host today's session. See you all soon.
See you all. Bye-bye.
Bye.